So, dear students, I hope all of you are fine. And here in this video, I'll be talking about the characteristics of an ideal operational amplifier. So, if I go with the symbolic presentation of an operational amplifier, this is an operational amplifier, open-ended. It has just two inputs, V1 as positive and V2 as negative, and it has biasing voltages as plus V and minus V. And here we have output voltage of this operational amplifier. Now, the very first important point about this operational amplifier is uh, that the open loop gain of this ideal amplifier is infinite. So that should be the first important point regarding the characteristics of an ideal operational amplifier. What it means is that if we talk in terms of voltage gain, it must have infinite voltage gain with respect to the inputs as an ideal amplifier, as an ideal operational amplifier. The next important thing about this operational amplifier is that it must have some kind of resistance, right? So let me assume that, and the input resistance of uh, uh, this operational amplifier, input resistance, or we may say impedance. It must be infinite for an ideal operational amplifier. Cannot be infinite, but for an ideal operational amplifier, its value should be infinite, and practically its value is very high. Now, if this is the case, say for example, we have the current here, I'll call it, say, IB1. Here I call the current as IB2. Now, if this is the case, that the input impedance of this operational amplifier is very large, in that case, if we think in terms of Ohm's law, V is IR, or Z, you can say. So this R is sorry, this I is V by R. Now, if we choose this R, the resistance, or we can say impedance, if we choose it extremely large, so that it's infinite, in that case, the current will be zero. So I'll say that the current that will pass through the resistance of this operational amplifier will be zero, right? So this is another important characteristic of an operational amplifier. And 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 about its output, I mean, the output impedance of the operational amplifier should ideally be equal to zero. So that's another important point, that this output impedance should be ideally equal to zero. And then the next point is uh, this operational amplifier has something what is called as zero offset voltage. Zero offset voltage, and we will try to define this zero offset voltage. Now, we have two inputs for this operational amplifier. One is V1 and then is V2. Now, if we have a condition where we say that V1 is equal to V2 is equal to 0, then if we have to write the gain of this operational amplifier, so that gain is something like this: AD times uh, V1 minus V2. So in this case, we should be able to find VD equal to 0, right? Now this VD is my output voltage, right? This VD is output voltage. So ideally the output voltage of this kind of system should be equal to 0. But that's not the case. So this VD should be ideally equal to 0, or V out, you may also call it. But some voltage is found, and some voltage is found in the output. The voltage that we found under those circumstances, when V1 is equal to V2 is equal to 0, we call that voltage as offset voltage. So that voltage that we have, we call that offset voltage. For ideal operational amplifier, it has to be 0, and but we don't find 0. We always find some voltage, and that voltage we call as offset voltage. Now there is another important point, another important characteristic that's linked with this operational amplifier, is that for an ideal operational amplifier, it must have infinite bandwidth. That means it should be capable of amplifying all the frequencies. I mean, all the frequencies. The signals that are subjected to this ideal operational amplifier having different frequencies. The ideal operational amplifier should be in a position to amplify all of the frequencies that are present present in the input. And then after that we have CMRR. And what is this CMRR? We have defined it in previous video. The CMRR is common mode rejection ratio, and this common mode rejection ratio for an ideal operational amplifier, it should be infinite. And we have already defined this CMMR. It's the ability of the operational amplifier to reject to reject the noise that develops in an operational amplifier. Or we should say the unwanted signal that's present in the output. So for an ideal operational amplifier, this CMRR, it should be equal to 0. And then after this, we can say we have another characteristic property of an ideal operational amplifier, and that's called the slew rate. And this slew rate should be infinite. It should be infinite for an ideal operational amplifier. And how do we define this slew rate? Let us assume that it has a symbol S. Then this slew rate is defined as the time derivative of output voltage, right? So time derivative of output voltage is defined as the slew rate. And for an ideal operational amplifier, its value should be infinite, and we can see it can be measured in volts per second, right? Then after this we have another important concept that's linked with the operational amplifiers. And what is that concept is that if we have an operational amplifier, and we think in terms of what we have defined till now. This is V out, this is V1, and this is V2. This is the positive terminal, this is the negative terminal. And we are well aware about the positive and negative. This terminal is non-inverting terminal, and this negative terminal is an inverting terminal. Now, since this the input impedance of this operational amplifier is infinite. Now, if that's the case, okay, it is infinite, and if it is infinite, then we better understand that the current passing through this input impedance must be equal to zero. And so here it's a kind of situation that, suppose if I take on this V1 and I ground it, and I take on this V2 and I ground it. Okay, now if I do that, since I understand that the input impedance of this operation amplifier is large, extremely large, in that case, I can say that this V1 is equal to V2, right? The potential the potential that's that with respect to the positive terminal, and the potential with respect to the negative terminal, the two potentials must be same. Now this condition is defined as the virtual ground, the virtual ground of an operational amplifier. So there are two important things that we have to bear in mind. That is, the input impedance of the operational amplifier is very large. So if we think of a resistance here between this and this, the current that will pass through this resistance should be practically taken equal to zero, right? And we call it virtual short. And at the same time, if we ground the two terminals V1 and V2, then under the given condition, under the given circumstances, the potential that we have at V1 must be equal to the potential uh, at V2. So V1 should be equal to V2. Now the ground that we have defined here, we call this ground as virtual ground.